In our previous lecture, we were discussing the effect of round off errors in numerical differentiation. We were illustrating the same through an example. Now, let us just review our discussion of the example and study the effect of the round off errors. Now, what we were considering were the computation of the second derivative in the using the formula f double dash x naught is approximately 1 upon h squared f of x 2 minus twice f of x 1 plus f of x 0. Now, we have shown that the truncation error in this formula can be written as truncation error is h times f triple dash of xi lying between x naught and x 2. We have also shown that the round off error is given by 1 upon h square of epsilon 2 minus twice epsilon 1 plus epsilon 0, where epsilon 1, epsilon 1 and 2 are the round off errors in f x naught, f x 1 and f x 2. Then we have taken the magnitude of this and shown that the magnitude of the truncation error is less than or equal to h times m 3, where m 3 is the maximum magnitude of f triple dash x is equal to the maximum on the given interval x naught to x 2. Then we have taken the round off error and written the bound of the round off error as less than or equal to, we have maximized these ones and taken it as epsilon plus 2 epsilon plus epsilon, that is 4 times epsilon upon h square, where epsilon is the maximum of the magnitudes of these 3 round off errors. Then I can write down the round off error is bounded by this. Then we made the observation that as h tends to 0, that is your convergence problem, then truncation error goes to 0. However, because of the appearance of h square in the denominator, round off error goes to infinity or goes unbounded. So, as h tends to 0, truncation error goes to 0 and round off error goes to infinity, or we can say it becomes unbounded, as h goes to very small quantity. Now, let us just have a look at these two values. Let us try to draw a graph of the round off error and truncation error with respect to the step length h. Let us draw the graph of this. So, I will take along this h, and on this side I will take either the round off error or the truncation error. Now, if I take the truncation error for a given h, it has got a certain value. Let us suppose I choose a value of h over here and I have a value truncation error here. As h goes to 0, that means h comes towards the origin, this truncation error goes to 0. Therefore, the graph of the truncation error will be something like that. It is coming to 0 as h tends to 0. Now, this is the graph of truncation error. Now, if I draw the graph of the round off error for some value of h, it has got some value over here, the round off error is corresponding value of this h, we take this as this. As h goes to 0, this round off error grows. So, the round off error now grows and goes like this. So, this is the magnitude of round off error. Now, this is the behavior of the round off error, h tends to 0, whereas truncation error goes to 0 and round off error becomes unbounded as it goes to 0. Therefore, this tells us that there can be a value of h such that for h smaller than that value, say optimal value, the round off error dominates the truncation error. Therefore, round off error dominates the truncation error, and hence after few more values of h, it is going to completely get unbounded. That means, we can say there exists a value of h here. So, let us call it as h optimum such that for h less than h optimum, the round off error dominates the truncation error. And therefore, this leads to a numerical instability. Now, how do we find this H optimum? There are two ways of dealing with this problem. For example, if you look at this graph, we find that there is a point at which these two graphs cut, that is at the point where the truncation and round off error are equal. So, I can call this value as an H optimal value, where the truncation error, the magnitude of the truncation error and round off error are equal. So, we can say find H such that magnitude of round off error is equal to magnitude of truncation error. Alternately, you can look at in a different direction, you can ask find H such that the total error is minimum, that means sum of round off error and the truncation error is minimum. So, we can also use this criteria and say find H such that total error is minimum. That means, we are talking of magnitude of round off error plus magnitude of truncation error is minimum. Now, this will complete tell us the why we are talking of possibility of numerical instability in the numerical differentiation methods. Now, let us use this first criteria for the problem that we are just now discussing. So, let us go back to this to find this. Now, magnitude of round off error is equal to magnitude of truncation error. Therefore, I need to have 4 epsilon by h square is equal to h into m3. So, that is 4 epsilon upon h square is equal to h into m3. Now, I can multiply it out and write this as h cubed is 4 epsilon upon m3. Therefore, I can find the value of h from here. Therefore, h optimal value is equal to 4 epsilon upon m3 to the power of 1 by 3. Now, let us see what is the error here. The error is magnitude of round off error is equal to magnitude of truncation error. If we can use any one of them, that is your 4 epsilon upon h square, suppose I use this the left hand side, that will be equal to 4 epsilon h squared 1 upon h square. So, I can invert this and take to the power of square. So, I can invert this as m3 upon 4 epsilon and write this as 2 by 3. So, this is 4, this is divided by 4 to the power of 2 by 3. So, I will have 4 to the power of 1 by 3, I have m3 to the power of 2 by 3 and this is epsilon and epsilon 2 by 3. So, I will have here epsilon to the power of 1 by 3. Now, you can see the effect of the round off error. If in a particular problem you have said that your maximum round off error is 1 into 10 to the power of minus 6, that is your results is accurate to 6 decimal places in the data, then I find that the error is of the order of epsilon to the power of 1 by 3. So, the error is going to be of the order of epsilon to the power of 1 by 3 is of the order of 10 to the power of minus 2, cube root of 10 to the power of minus 6. So, we will have 10 to the power of minus 2. Now, you see how much is round off error has eaten away your decimal places. There were 6 place accuracy initially, and we find that the derivative, second derivative is now we can guarantee only 2 decimal places, that is 10 to the power of minus 2 is beyond that there is error. Therefore, we can guarantee only. Therefore, 4 decimal places have really been destroyed because of the round off error. So, this is where the numerical instability can arise in numerical differentiation. Now, if I leave this as an example for you, let us look at the second part. The second way of looking it is magnitude of round off error plus magnitude of truncation error is minimum. Therefore, I can add these two quantities and make this minimize it. So, I will have 4 times epsilon upon h square plus h times m 3 is minimum. So, I can differentiate with respect to h and then find out the minimum value. So, this will give us minus 8 epsilon upon h cubed plus m 3 is equal to 0. Therefore, I can find out h cubed from here. I would go to this side and write this as 8 epsilon upon m 3. So, that h is now 8 epsilon upon m 3 to the power of 1 by 3. Now, this is the now we can find what is the total error. Now, this is h times m 3. So, this is simply epsilon to the power of 1 by 3, this is also epsilon to the power of 1 by 3, just sum up and show it, and again I have this as epsilon 1 by 3, except that the constant that is multiplying this factor is different from what we have in the previous example. Therefore, even though we make the sum of these errors is a minimum, even then we are still not improving the result substantially, except that this figure that we are now having, that is constant that is multiplying, may be smaller in one case and bigger in the other case. Therefore, this is how the loss of the significant digits can obtain in the numerical differentiation. Now, given any formula for us, the procedure for doing this is just write down what is the truncation error, just write down the round off error and then apply this particular rule to find out what should be the step length or h optimum such that the round off error is controlled. Now, if this is the difficulty in numerical differentiation, what should be the alternative to get better results? If I can take a higher order formula by including more number of points, that means instead of in this case we had f naught f 1 f 2, instead of having f naught f 1 f 2 I can include few more points f 3 f 4 f 5, so that I can have the formula for first derivative or second derivative which will be higher order than this, because I am using. But then if I once I introduce more number of ordinates here, automatically I am introducing the round off error by few more. So, instead of 4 epsilon it could become 6 epsilon. So, the factor that we are multiplying can go higher in this particular case. Second observation is, suppose that in a practical problem you really do not know what is the function that is governing the data, we did not know what is its derivative, first derivative, second derivative and so on. So, in practice what we normally do in any problem is that you solve the problem with a particular step length h, we are not sure that the result is good or not. So, we repeat the same computation with another step length say smaller than that. If you have started with say 0.5, you may integrate again, solve it, use it by again 0.25 or so. If the magnitude of the difference between the two results is less than tolerance, we accept that the result is good. Now, if this difference is greater than the tolerance which you have, what do? We have to go further down one more step length and then see how the result is. Now, in this procedure we have already spent a lot of computer time in evaluating the first result, evaluating the second result, now we are computing third result. Now, the question is, can we use these results that you have already computed and which are of no use for us because they are not accurate enough, can we use these results that have been obtained from the computer to manipulate a result which will give you better result than what we have obtained from these two results? The answer is yes, it is possible for us to manipulate those results which we think they are useless, but they can be manipulated to get a result which will behave as if it has been obtained by a higher order formula and not by present formula that we are using it, and that is called the Richardson's extrapolation. So, let us discuss what is Richardson's extrapolation. This is sometimes simply called extrapolation. We may not use the word Richardson, we may simply call it as extrapolation. Let us generalize this Richardson extrapolation, whether we can use it for the first derivative, second derivative or any derivative. In fact, we are going to use this in numerical integration also, the same procedure, extrapolation. What we have here is, we suppose let us just call G, suppose G is the quantity being determined. Be determined by a method of, let us choose a method by a method of order p. So, with a step length h. Now, we can identify this quantity being determined as first derivative, second derivative or any derivative. So, we can identify it as first derivative, second derivative or any one of them. Therefore, what we have it is g h, that means g obtained with step length h is a g exact, E for exact, let us denote g E for exact, that is the exact quantity g that is being determined. I add to this the truncation error that we have method of order p, therefore, C h to the power of p plus order of h to the power of p plus 1. I added truncation error to the exact solution or to the numerical solution to get this as the expression for the exact solution. Now, we repeat this computation with one more step length, repeat with step length, repeat the computation with step length. Let us take q times h and we take q smaller than 1. So, that we are now decreasing the step length. Now, therefore, this equation 1 will now read as g q h is equal to g exact, that remains as it is, C q times h to the power of p plus order of q times h to the power of p plus 1. So, let us repeat this g exact C q to the power of p h to the power of p order of h to the power of p plus 1. This q to the power of p plus 1 is a number which can be absorbed in this order. So, we absorb it and write it as simply order of h to the power of p plus 1. Therefore, we now have two computed results. One result is g of h that has been computed, another result g of q f of h has been computed. Now, let us write down the equation 2 as, let us bring this g e to the left hand side, that is g q h minus g e and divide by q to the power of p, that will be c h to the power of p plus order of h to the power of p plus 1. I bring this to the left hand side and divide by q to the power of p, this one. Now, let us write down the first equation also again, g of h minus g of e is c h to the power of p plus order of h to the power of p plus 1. Now, if I subtract these two results, then c h to the power of p gets eliminated. So, therefore, I have got g q h minus g a by q to the power of p minus g h minus g e is equal to order of h to the power of p plus 1. Now, c h to the power of p has been cancelled. Now, let us simplify this. This is g q h minus, I will first write this q to the power of p into g of h. I multiplied this and combined this, then this is plus q to the power of p into g of e minus 1 of g e. Now, if I divide throughout by q to the power of p minus 1, I would have the expression g q h minus q to the power of h g of h divide by q to the power of p minus 1 plus g of E is order of h to the power of p plus 1. Now, if I take it to this to the right hand side and approximate it this as the new value, g of E is the value that is being computed, that is the exact value that is being. So, I can approximate by this quantity, I take it to the right hand side. So, I will make this as plus sign q to the power of p g h minus g of q h divided by q to the power of p minus 1, and the error is now order of p plus 1. Now, you see the interesting thing, g of h is the computed result, g of q h is also computed result, q is the number that we already know, q is the number that we have reduced the step length, that is q into h. So, q is also known quantity. So, all the quantity here is completely known. Now, I have got the new approximation for the g exact as this particular quantity, and what is the order of the method? The order of the method is p plus 1. Therefore, I have manipulated two computed results to get a result which is one order higher than the previous one. So, it behaves as if you have obtained the higher order method. Now, if you can go back into the formula that we have, if you have used a 3-point formula, and if I want a higher order, I need to add one more point or two more points to get the higher order formula. That means, it is as if you are using more number of points and getting better results. For example, if you have decreased by a factor of 2, that means q is equal to half, that means we are using step length as h and h by 2, then this will read as g of E, and let us equate it as g 1 of h. So, we would call this as the approximation as superfix 1, and this the initial ones we will take it as g 0, and this is equal to g of h minus 2 to the power of p g of h by 2 by 1 minus 2 to the power of p. This is 1 upon 2 to the power of p, I have multiplied it, and 1 upon 2 to the power of p, I have cancelled off 2 to the power of p. This we can write as 2 to the power of t h by 2 minus g h upon 2 to the power of p minus 1. Now, you can see the coefficients, if you look at the coefficients in the numerator, q to the power of p and minus 1, denominator is q to the power of p minus 1. The denominator is just the sum of the coefficients in the numerator in this formula. This is called the Richardson extrapolation formula. Now, if I repeat the next computation with one more step length, I can again do the same manipulation with respect to two successive values and get a method as if it is obtained by the next higher order. Now, let us write down what it would look like if I write this in a sequence. I will call this as extrapolation table. Extrapolation table. So, let us start with a pth order formula that we started with, and we have computed g of h, we have computed g of h by 2, let us say we have computed g of h upon 2 square, and let us say g of h upon 2 cubed. Let us suppose that we have the computations, 4 computations we have done. Now, if I manipulate these two computations, which I am denoting as g 1 of h, that is 2 to the power of p, I am taking the 1 upon 2 square. Therefore, this will be 2 to the power of p g of h by 2 minus 1 into g of h by 2 to the power of p minus 1. Now, this will be as if this has been obtained from a p plus 1th order formula. It would behave as if it has been obtained from a p plus 1th order formula. I can manipulate these two successive ones and call this as g 1 h by 2. The coefficients do not change, 2 to the power of p g of h by 4 minus g of h by 2, these are the two successive values that we are using, divided by 2 to the power of p minus 1. if I manipulate these two, again I will have g of 1, I will now call this as h upon 4, this is 2 to the power of p g of h upon 8 minus g h upon 4 divided by 2 to the power of p minus 1. Now, all these three results are of p plus 1th order, the last one being the best value, because this is h smaller h smaller h. So, this last value is the best in this column and this last value is the best in this column. Now, since the method is of p plus 1th order, that is h to the power of p plus 1, I can now similarly manipulate exactly the same way that we have done, but now the coefficients are going to be 2 to the power p plus 1 and minus 1, because the method is of order p plus 1th order. So, now if I reduce h by 2, h to the power of p plus 1 divided by 2 to the power of p plus 1. So, we have to eliminate that particular coefficient. So, I have to multiply by 2 to the power of p plus 1. So, I can now have here g 2 of h, we will write down the value in the next page. So, g 2 of h by 2. So, this behaves like p plus 2th order formula, where that g 2 h is equal to 2 to the power of p plus 1 g 1, that we are now computing this g 1 of h by 2 minus g 1 of h, that is this and this, divided by 2 to the power of p plus 1 minus 1. And similarly, g 2 h by 2 is 2 to the power of p plus 1 g 1 h by 4 minus this value, the previous value g 1 h by 2 by 2 to the power of p plus 1 minus 1. Now, depending on the number of computations that we have done, we can complete the table until we get one value. Now, I can use these two and then get, I will write it here, g 3 of h, and which will behave like a p plus 3rd order formula, where now we are eliminating the method of order p plus 2, that is order of h to the power of p plus 2. Therefore, the next coefficients will be 2 to the power of p plus 2 minus 1. So, I would therefore have the next computation g 3 of h is 2 to the power of p plus 2 g 1 g 2 h by 2 minus g 2 of h, that is we are now manipulating these two values, divided by 2 to the power of p plus 2 minus 1. Let us now take an example for application. Example: derive an extrapolation formula for the numerical differentiation rule f prime at x naught is approximately equal to 1 upon 2 h f x naught plus h minus f x naught minus h. Now, in the notation that we have used earlier, let f dash at x naught be denoted by g exact. That means, we are writing g exact and let us call it as g of e is equal to f prime of x naught. Now, let us find the truncation error of this rule. Now, we write 1 upon 2 h f of x naught plus h minus f of x naught minus h. We expand f x naught plus h and f x naught minus h in Taylor series, simplify and then collect the terms. Hence, we have 1 upon 2 h f of x naught plus h f dash of x naught plus h square by factorial to f double dash at x naught plus h cubed by factorial 3 f triple prime at x naught h 4 by factorial 4 f 4 of x naught minus f of x naught minus h f prime at x naught plus h square by factorial to f double prime at x naught plus h cubed by factorial 3 minus h cubed by factorial 3 f triple dash at x naught plus h 4 by factorial 4 f 4 x naught and so on. Now, we can see f of x naught cancels with f of x naught, second derivative terms cancel, fourth derivative term cancel and the first derivative term add up, third derivative term adds up to gives us 2 times of these terms. Now, we cancel 2 times h, then we would produce here f prime at x naught plus some c 1 h square plus c 2 h to the power of 4 plus c 3 h to the power of 6 and so on. Now, numerical solution is equal to exact solution plus truncation error, or exact solution is numerical solution plus truncation error. So, let us write down the numerical solution is equal to exact solution plus truncation error. Therefore, if I denote g of h by the numerical solution, I can write this as g of exact plus these error terms c 1 h square plus c 2 h to the power of 4 plus c 3 h to the power of 6. Now, we need to take the step lengths starting with step length h and then decrease it further. For our discussion, we shall take the remaining step lengths as h by 2, h by 2 square, h by 2 cubed and so on. Therefore, we use the step lengths as h, h by 2, h by 2 squared and so on, h upon 2 k and so on. Now, I can set h is equal to h by 2, h is h by 4 in this equation and then write down what would be the expressions in that case. Then we get here g of h by 2 is equal to g of e plus c 1 h square by 2 square, that is 4 plus c 2 h to the power of 4 by 2 to the power of 4 16 plus c 3 h to the power of 6 by 64 and so on. G of h by 4 is g of e plus c 1 upon 4 square, that gives you h square by 16. Then I have 4 to the power of 4 h to the power of 4 by 256 plus c 3 h to the power of 6 by 4 to the power of 6, that is 4096. Now, let us stop here and then write down, derive our extrapolation formula. Now, I would use equations 1 and 2, I will use equation 1 and 2 and eliminate c 1 h square from this. Now, we can see if I multiply this equation by 4 and subtract this, then c 1 h square cancels. Therefore, I would write down 4 into equation 2 minus equation 1. Then I get 4 g h by 2 minus g of h is equal to 4 minus 1, I will retain it in this particular form, yes, plus this has cancelled. Now, I multiplied this by 4, therefore, this is 1 by 4 minus 1. So, I will get minus 3 by 4. So, I will have minus 3 by 4 c 2 h to the power of 4 plus order of h to the power of 6. So, let us write for the moment order of h to the power of 6. Now, similarly, Now, I will write down what is my g of E. G of E is 4 times g h by 2 minus g of h divided by 4 minus 1. So, I find the value of g E by just dividing by 4 minus 1, and this I will denote it by g 1 of h. Now, here h square term has been removed, therefore, this result would behave like an order of h to the power of 4 result. Therefore, this value is of the order of h to the power of 4. Hence, I can write g 1 h is equal to g E minus I divided by 3. Therefore, I will have here 1 by 4 C 2 h to the power of 4 plus some C 3 star h to the power of 6 plus so on. Now, I would eliminate similarly C 1 h square from C 1 h square from equations 2 and 3. Therefore, again you can see I multiply this by 4, then I subtract this equation, I would then again cancel this. Therefore, I have 4 g h by 4 minus g h by 2 is 4 minus 1 of g of E. Now, this has cancelled, this is 1 upon 64 minus 1 upon 16. Therefore, I would then have the required term as minus 3 by 64 C 2 h to the power of 4 plus some C 3 prime h 6 and so on. Now, I can determine G E from here again. G E is equal to 4 into G h by 4 minus G h by 2 divided by 4 minus 1, and this I will denote it as G 1 of h by 2. Now, again C 1 h square has been removed from here. Therefore, this result again behaves like a 4th order results. Therefore, this is also of order of h to the power of 4, and G 1 h by 2 is G of E minus I have divided by 3. Therefore, I will have C 2 by 64 h to the power of 4 plus some C 3 double prime h to the power of 6 and so on. Let us number this 4, number this as 5. Now, I would eliminate C 2 h 4 from these two equations. I would now eliminate C 2 h to the power of 4 from this equation and this equation. Now, you can see if I multiply this by 16 and subtract from this, then C 2 h 4 cancels from here. Therefore, I will have here 16, that is 4 square G 1 h by 2 minus G 1 of h will be equal to 4 square minus 1 of G E, this and this, plus order of h to the power of 6. Now, I solve for G E from here. Therefore, I will get here G E is equal to 4 square G 1 h by 2 minus G 1 of h divided by 4 square minus 1. This we can write it as G 2 of h. Now, the previous two values have given us the first two elements of the second column of the extrapolation table. This gives me the first element of the third column of the extrapolation table. Now, I can continue this procedure and then arrive at the formula that G of m h. I am now writing the column of this G m h is equal to 4 to the power of m G m minus 1 h by 2 minus G m minus 1 of h by 4 to the power of m minus 1. M is equal to 1, 2, 3 and so on. Now, let us take an example on this. The following table values of given. the following table values are is given. X f x minus 1 1 17 240 3 173 4 526 5 1267 7 4825. Using the formula f dash of x 1 is 1 upon 2 h f 2 minus f 0 and Richardson extrapolation. Find f dash of 3, find f dash of 3. We are given 7 values in the table and we are using the central difference approximation and the Richardson extrapolation to find the derivative at the point 3. Now, this is the example which we have just now discussed, that is why I written it, but however the first step for you would be to first Taylor expand this, write down what is the error in this formula. So, we know that the error in this formula is of the order of C 1 h squared, C 2 h to the power of 4
plus C 3 h to the power of 6 and so on. It is a central difference formula which is symmetric about x 1.
So, we have this. So, the table that we have given earlier, that we shall use this. Therefore, our formula would be that 4 to the power of m g of h by 2 minus g of h divided by 4 of m. This is our the formula that we shall use in the table. Now, we have been asked to use the Richardson extrapolation and therefore, we must be able to compute the derivative using a particular step length. Let us see what are the possible step lengths that we have here. So, we are you to use f of x 0 plus h, f of x 1 plus h, x 1 minus h. This is our point. Now, you can see 7 is here which is at a distance of 4. Now, if there is a value available for us at a distance 4 behind, I can use the formula.
This is 4 ahead and this is 4 behind.
So, I can use these two values with a step length of h is equal to 4. I can use h is equal to 4 and get an approximation for this. Now, with 3, 5 is also given which is a distance of 2 and at a distance of 2 behind also is given to us. So, I can also compute with h is equal to 2. Now, again 4 is given at a distance of 1 ahead and I have a distance 1 behind also is given to us. That means, I can also compute with h is equal to 1. Therefore, I have got 3 possible values of h that can be computed, h is 4, h is equal to 2 and h is equal to 1 and each one is reduced by factor of 2. So, again is reduced to a factor of 2, so that I can use this particular formula that we have used. This is only for the case when you are reducing by factor of 2. Now, let us write down the solution. So, let us take h is equal to 4 and the formula that is given is the starting computation is order of h square formula.
The leading term is order of h square, that is a second order method.
H is equal to 4. Now, what is the value? F of 2 is equal to 4825 minus 1, this is f of x 2 minus f at x 0 divided by 2 times h, h is equal to 4, that is equal to by 8. Therefore, 603. Now, let us use with step length 2. With step length 2, f of x 2 will be 1267. So, this will be 1267 and the value f naught will be 2 steps behind, that is 7 minus 7 divided by 2 times h, h is now 2, that is divided by 4. 1260 divided by 4, that is 315. Now we have step length 1. With step length 1, the value at the next point is 526 minus 40 divided by 2 times h, that is 2, that is 486 by 2, that is 243. Now I would like to manipulate this column. Now of all this, the best value in this column will be this, because this is the best value of h. Now the next order formula will be order of h to the power of 4, because the next order in this is h to the power of 4. So it will behave like the 4th order formula. And what is the value? This is 4 times 315 minus 603, 4 times this value minus this value, divided by 4 minus 1, that is equal to 3. This gives us 219. And now I have 4 times 243 minus 315 divided by 3. No, this is your this is your basic numerical method that we have used. Now we are starting, yes, this is 4, this is m is equal to 1, you have got 4 times g of h by 2 minus g of h divided by 4 to the power of 1 minus 1, that is 3, and this is also equal to 3. This is also equal to 219. It turns out that it is also equal to 219. Now let us write down, complete this table, order of h to the power of 6. The next term in the series is h to the power of 6. Now let us, we will write down the value here, let us write it here. This will be 4 square, that is 16 times 219, 4 square, that is 16 times this, minus 219 divided by 16 minus 1, that is equal to 15, and this of course is again 219, 16 minus 1 by 15. So this is again 219. Now in this column this is the best value, in this column this is the best value. Two successive approximations have become identical, that means this is your exact solution, because 219 219, two successive approximations identical, the difference between them is 0, therefore error is here 0. Therefore what we have got here is the exact solution. Otherwise our best solutions will be going up in this direction. The last value in this column is the best, last value in this column is the best, the last value in this column is best, and so on. So we have the best approximations going in this direction. In fact in most of the problems Richardson extrapolation really works wonders, because the the values which were so much away from the exact solution, this is 603, this is exact solution is 219, we are able to manipulate these results which are so bad to get the results which are very very accurate, and this is, we are now getting the values as if they have been obtained by order of h to the power of 4, order of h to the power of 6, and so on. By just getting 3 values I am getting a value as if it has been obtained by order of h to the power of 6. Now if I want to write down a formula of h to the power of 6 using this, I need at least 9 points or so, therefore round of error will be more. Sorry. Therefore the most important tool in getting better results is Richardson extrapolation for numerical differentiation.